Hello everybody. My name is Coulibaly, and today I'm going to make the presentation of traveling salesman problem solved in genetic algorithm. First of all, I want to make the introduction of my functions and important variables. First of all, the first function is equate population. It has the size of population size, and then I get a list of all the cities, then shuffle, then create an individual out of the cities, then append that individual to the population, then return the population. The second function is calculate distance. Here I calculate the equation distance according to the order. Here it will get a list, then according to the order calculate the equation distance. Uh, Here we can see that it will get an element. Here it will get an element and get the element next to that element, then calculate the equation distance between the two elements, which is x1 minus x2 squared plus y1 minus y2 squared in the square root, then return the sum. After that, I calculate the fitness. Fitness represent the distance of every individual. Yeah, so I loop through my population, then calculate the equation distance of the path, I can say, of every individuals. Then check that if d is less than our record distance, that means record distance is equal to d. And then yeah, there is ulti-best. Ulti-best is the best individual ever that can exist. So if this condition is true, then ulti-best is equal to that individual. So we have a we can say yeah, we'll have an ulti-best here. Then append the distance to the fitness. The property of fitness is that uh, the bigger distance it is, the less fit it is, and the less distance it has, the fitter it is. So that's why I inverse the distance here and just multiply by 1000. It is not obligatory, this thing, and then I return the fitness. Next function is get fittest. Get fittest. Uh, where is it? Yeah, it get the fittest out of uh, every individuals in the population. So it get population here, then it will evaluate, then return the best individual out of a population, then return fittest. Yeah, after I get fittest, there is a function called tournament selection, which return the parent, we can say. It get a population, then choose an element that will be considered as a parent. Here we look through the population, then generate a random number, which name is random ID, then get that individual from the population, then append it to our tournament. And then the tournament selection return, uh, we want our parent to be a good element, so it will return the fittest out of that tournament. Uh, After that, we make the crossover. Let me introduce the crossover function. Yeah, crossover will get uh, two parents, then make two offsprings out of the parents, or we can say get two parents and return two children out of it. Let me make a test from here. Uh, yeah, yeah, we have some random list. This sample will create a list of five elements, a list of five elements that contains a number, random number from 0 to 10. This also get return a list of five elements. The elements are between 0 to 10. And here we have the parents and apply the crossover. We have child 1 and child 2. Let's run that and see. Yeah, we have our parent 1, which is this one, and parent 2, which is this one, and we have our start, which is equal to 2. Yeah, so we have 0, 1, 2. So we start from 3 and get 9, and then 4. We can see offspring 1, uh, 3, 9, 4. And after that, we will add some elements from the parent 2 also. So we have these first three elements that are from parent 1. Then I will check if 3 is not in here, then append 3. But we can see that we already had 3, so it will check 2, and we can see that 2 is not here, so append 2, and we check if 1 is in here. 1 is not, so it will add 1 from parent 2. And the second offspring will also, we have start 2, so 0, 1, 2. So 1, 7, 0. We can see 1, 7, 0. Then it will check if 2 is in this, it will not add. So we can see that 2 is not, so it will add 2, and it will check 0. 0 is in it, so it will not add 0, so it will take 3, then add 3. So that's the logical between uh, the crossover function. Next is making mutation. Mutation, I used the swap mutation, which will get uh, an element, then choose two random index. I create two random index here, then swap these two, the elements that are in these two indexes, and then it will swap. I called the swap function here, then swap that. And let's check here. No, this one. Yeah. Here we have, uh, uh, as I said, I create a random list, so it has 6, 1, 5, 0, 3. Then after mutation, we will see that 1 and 5 have changed, has been interchanged. So 5 take the place of 1 and 1 take the place of 5. And also the mutation also depend to the mutation rate. Yeah. So if we generally want the rate to be low. So let's just say 0.5. Yeah, here we can see 2 and 0 have been interchanged. Here there is no change, here not. Yeah, here we can see uh, 4, 7 and 1 have been interchanged. So this is the logic of mutation. 1 take the place of 7 and 7 take the place of 1. Yeah, after I make the mutation, now I create a new generation. Creating new generation, where is that function? Yeah, I create a new population, and then I loop through the old population or the population I already had. I will say parent is equal to tournament population. As I said, a tournament selection is for choosing a parent. Parent 1 is equal to that. Then parent 2 here. Then I get the keys because I have dictionaries. Then I say crossover parent 1 and parent 2. Then I will get child 1 and child 2, or offspring 1 and offspring 2. Then make mutation. I make mutation with this mutation rate. Mutation rate is probabilistic, so sometimes change happen, sometimes not. It's a little bit random. And then uh, I get the minimum, or I can say the child that has the less of the child that has the less of distance. I return that with get min function. I return the child, the better child. Then I append that child to my new population. Then after the loop is over, I say my population is equal to the new population. Yeah. Okay. Now let's make an evaluation. I declare some variables: record distance, ultimate base, and an empty list of population. And I say population size is equal to let's say 10 for this one, and then iteration, the number of iteration, let's say 100, and then I will get, oh, I forgot to show that. I'll read the file ch150.tsp, which is here. I get the element, I get the coordinates like that. Yeah, I get the coordinates and I round them. Then I put them in a dictionary according to their indexes. So I get all the cities from them. Then I say cities is equal to nodes dot values. It will get the values of our dictionary. Then here I say test dict is it will take the first 10 elements. For example, we can say it will get these 10 elements. Yeah. Then let's run our program, and here I draw the best ever. Every time I draw the best ever, and here in this iteration I print the best ever. Okay, let's run and see. Yeah, here we can see that after running the program, you can see the best ever is improving by the time. Here from 2381 to 1918. So we can see through the iteration it will improve. Then my final value will be this. Yeah, we can see that it is not bad. It's not bad. It will return like that. And now let's change our values and say number of iteration is equal to 200, and we get the first 20 elements from our cities. Yeah, we can see the improvement in our best ever solution. Yeah, to have 2000. Yeah. Uh, yeah, we can see that it is not the best of solutions, but here there can still be some improvements here. So let's change this to 500 and see. Take a little bit of time because there are so many iterations to be done. Yeah, here we have a better solution than the previous one we had. So that's the idea of the algorithm. Yeah, and for the all the cities we have uh, as you said, to take 10,000 of iteration. Then here I will get all the elements 150, because we have 150 places to visit, and I say a population size is equal to 50. Then let me run and see. We can check the changement in the, yeah, we can see the improvement in the best ever solution. So this will take hours and hours of iteration, but after all this, I get an answers. Yeah, I get something like this with 7,226. Yeah, that's it. Thank you for listening. Yeah, you can still see the improvement. Yeah, that's all for this. Thank you for listening.